So high index would be it bends light more. And then low Abbe number would be higher dispersion. It's just kind of backwards, but higher dispersion means it separates colors more.
Okay.
So you can use that in color correction because all the glass is going to separate colors to some amount. And optical design, it's not like making every lens perfect individually. You're making something that's well balanced.
All right, how's it going, everybody? We're here. We got Jimmy and Mark on this side of the table, and across from us is optical engineer Christian Benson again. And I got the last name right?
Yep.
Because my email inbox, at one point, there was it was Denson. I knew that wasn't right. Anyway, so we're going to talk today about light transmission. Now, I'm really eager to talk about this topic with Christian, an optical engineer, because light transmission is a phrase that I see getting thrown around all over the internet. Everybody talks about light transmission, and I'm not always certain. I'm not always certain that when I'm talking about everybody out there who's talking about it, a lot of people might not know exactly what light transmission actually means. I think they have an idea in their head of something that they see, and they equate that in their head as light transmission. I'm also not even certain, I'll throw this out, that I know exactly what light transmission is and means and everything that goes along with that. So that's why we brought the optical engineer in. So here's another weird thing I'll throw out there, Marco.
Yeah.
For those watching on YouTube, this is a podcast that you're watching on YouTube. Now, a lot of people who subscribe to us already know that. Some people who stumble across this seem to think that we're trying to make a video, and they wonder why we have headsets on and whatnot. This is an audio podcast that gets thrown up on YouTube for those who prefer to listen to their podcasts on YouTube. So anyways, if you're watching and wondering what's with the headsets and all that, because I'm guessing a lot of people might Google what is light transmission and whatnot, and so this may pop up. So welcome.
I did, Jim, and you'll get
You sure did.
this many pages.
You sure did. There's a lot going on there. So Christian, I don't actually even know where to start, so to speak, with light transmission, because it's, again, like I said, people throw it out there all the time. I think a lot of times what people are trying to get at with light transmission is image brightness and how well an optic can do in low light scenarios. Particularly, a lot of hunters want to know this kind of thing. So they'll ask, I want the one with the best light transmission. I've seen percentages put on light transmission numbers. So I've seen where someone will say this scope has 90% light transmission. And then it's kind of a race to see who can find the biggest percentage of light transmission. I've seen scopes that list the lower light transmission percentages actually look better than scopes that list higher ones, and I've heard it's kind of the Wild West in terms of that. There's no real standard, and I don't know. Why don't you
People are measuring different things to come up with that number.
When an optical engineer hears light transmission, what goes through your head?
So you kind of mentioned some scopes having numbers, and maybe you compare two percentage numbers and it doesn't really line up with what you'd think of how much light's going through it. And so the first easy way to describe it is it's a percentage of the light that comes in and comes out. So if 50% of the light that came in comes out, then it's 50% light transmission. So it's kind of misrepresentative to just look at that number, because if you have a different objective size, let's say, and it's collecting more light from the target, you're starting out with more light, you might have a lower percentage. You might end up with more light coming from that object, making it look brighter. That's kind of simplifying it, but already it's kind of easy to see just from objective size. You can't just look at transmission number as the end-all be-all. That means more light's coming through it. From the optical standpoint, I saw some of your notes actually has kind of the breakdown of what's happening. So there's sort of three-ish things that happen that control transmission. So the light comes in, it can get reflected at the glass interface.
Okay.
Then when it goes through the glass, it gets absorbed. And then it has another air glass interface and can reflect again. So every single lens, you're losing light from reflection and absorption. Is the two biggest things, and those are taking away from transmission. So you start off with 100%. Every time you go through glass, some gets absorbed, some gets reflected off the surface. and then it just keeps happening as you go down the line.
Sure.
And then at the end, you kind of multiply out all those percentages, and you end up with some ending percentage, whatever it is.
And I've heard that even that is a bit of a simplification as well, because what you have is infinitely many spectrums of light that are all within the visible region for us in our human eye. And it may vary. Certain spectrums of light may be transmitting better through the glass than other spectrums of light. So if you measure a more red light and you say that has a higher percentage of transmission than this blue light, it depends on which spectrum you're talking about, really, right?
Absolutely. Yeah, so there's an anti-reflective coating that gets put on pretty much every lens. Kind of like a normal grade might be like 0.5% reflection, so less than 0.5% reflection across the visible range. But even within that, it's varying across wavelength, so that will affect what you're saying. But even more than that, absorption usually happens more in the blue. Just making sure I'm thinking about it right. Yeah, so it happens more in the blue. So you lose a lot more blue than you might red. So yes, if you just looked at your design and tried to calculate it out and then just picked a wavelength that you said that's the highest and I want to use that, it's kind of not representative of what it might look like.
Yeah.
And then there's other
wavelength,
things.
that's the word.
Wavelength, yeah.
Yeah.
And then there's other things that you kind of mentioned, low light performance. There's other things that also can affect the way that low light performance is other than transmission. You do want to get as much light through as possible. You can always think of things in extremes in optics to make it a little simpler. So if you had 1% transmission, you'd have to start with an extreme amount of light to compensate that, or you just look through it and it's really dark. So it's never going to really perform. So you do need transmission. But then if you have really good transmission, and let's say you have just a tiny objective, it's a pinhole, and no light goes in the first place, that also doesn't really help you either. So when you look at that, then maybe the next step is the actual correction of the optic. So if you have a bunch of light coming in, it's all going through, and it's all really blurry, that also doesn't help you. So you kind of just start building layers, because all these things are happening at the same time. They all need to be good for it to have good performance.
Because what good is it if something's super bright, but you can't even make out what it is?
Exactly. And especially when there's less light, I think it's harder to get a good contrast between different things, because it's not much light is coming off each thing. Contrast in optics is using intensity values, so max intensity minus minimum intensity, and then divided by max plus min. That's probably kind of complicated math, but so all that matters is it's max and min intensity. It's just looking at the brightest and the darkest thing for contrast between two things. That's the simple equation. But in low light, obviously everything's kind of trending toward the low value.
Yeah.
But contrast is relative to two values. But to get high contrast, you also need to have it be well corrected. There's less room for error, more or less.
Sure.
And then sort of the next thing that helps with low light would be something like stray light. So you've probably heard of that, but it's really easy if you use like your cell phone camera or something. Whenever you're taking a picture and you see like a big bright spot, or like what they call like a flare or a ghost.
Oh yeah.
The same thing happens to your eye if you're looking through and like the sun is just like right in angle or just above where you're looking, and you just see like maybe a bright spot or something. So that's going to decrease contrast more or less.
Sure.
So like if you're looking at a low light situation and your eyes sees like some stray light in there, it throws off your perception of being able to see the target. So so yeah, transmission is not the only thing. It just kind of adds up and it just gets really complicated. And then as the optical designer, you're just trying to work all these things together. And a great analogy that actually Dave, your brother, has used, but I think it might be common. You think of optical design like a blanket. You might reach a point and you're just kind of stretching the blanket in different directions. It can only get so tight, and then you're trying to make it better transmission, and then you're pulling something else away or whatever it is. So it's all these trade-offs.
Yeah, exactly. Trade-offs are a huge thing with optics, and it's funny. It's not to make fun of anybody who says this. It's everybody has these ideas of what they would like optics to do. We have ideas of what we'd like optics to do. But you see some comments out there, and a lot of people, well, it'd be really great if you guys could make a scope that was like 1 to 24, so that way I wouldn't need to choose from all these different options, and it was nice and lightweight, because I like the 24 millimeter objectives on the 1 to 6s, and I wish that it had like this, that, and they start kind of throwing their wish list of everything at it, and it's like, oh, I'm with you. That would be awesome.
Yeah, I want that too.
Yeah. So getting to light, when we talk about, light transmission stuff, I think one interesting thing that a lot of people, they oftentimes separate light from the image itself. And then I think it's easy to forget that actually the image you're seeing is light. And so I think a lot of people could just kind of assume like, yeah, there's an image there, and then however much my image brightness is just kind of like, it's almost like an overhead projector. Like there's an image there, and then you just kind of like crank it up and you make it really bright, or you make it dim. But the actual image itself is light. And so when we're out and it's, bluebird day, you're seeing everything really nicely, but you tend to, it seems you start to get, see the difference between optics, like really high-end optics and more entry-level optics. You really start to see the big differences when light is minimal, right? So as it starts to get darker outside. What is it that makes a more high-end optic? Like, for example, right in front of us, we have a Razor HD Gen 2, 3 to 18 by 50, really high-end optic. Excellent optical performance, all that stuff. So what is it that makes this thing so awesome in low light versus something that, here's another thing that gets me too. People throw around objective bell sizes, they throw on exit pupil numbers, all this stuff, right? There's a 3 to 18 here in front of us, Razor HD Gen 2. There's a 6 to 24. Actually, I'll even make it a little bit more of a direct comparison. There's a 6 to 24 by 50 Razor HD AMG rifle scope. So it's kind of similar to this Gen 2 in front of us, but a little bit different, some different features and stuff, different optical system. But it's a 6 to 24 by 50. And then there's a Crossfire 2 6 to 24 by 50, right? If you looked at them on paper, just those numbers and the numbers that you would use to get like an exit pupil, objective bell size. If you looked at those two on paper, you would say, yep, same light transmission.
Yep, ought to be the same.
Right, ought to be good to go, right? There's a $2,300 difference between those optics, and when you actually look behind the AMG 624, you see that in low light, it blows the other one out of the water. What's going on there? Why is one better than the other?
Yeah, there's a lot of things. It's kind of a combination of all the things I said before. The first order things, they help, I guess, to an extent. So you look at the objective size, but actually what plays into it also is the focal length of the objective. So similar to digital camera lenses, they are spec'd with an F number, and that kind of gives you the light collection ability.
Okay.
So it's actually easier to talk about an F number, which I don't know the focal length of every scope ever, so I can't necessarily calculate it, but I'm assuming the AMG has a wider field of view and probably a shorter focal length and probably is a smaller F number and is a faster system, meaning it's collecting more light. So that's kind of the first part of it. But then also, as you guys know, the AMG is much more corrected optically for resolution and contrast. So that's kind of the next step that plays into it. And then
when you say corrected, is that like something where you're on the computer as an optical engineer and you're like, okay, here's an optical system, and then you just click the correct it button, and then like,
bing. I think that's Control C, isn't it?
Oh, yeah. What when you say corrected, is that like go into lens shape, coating type, or?
It's mostly shape and glass type and spacing. And there is a funny joke that I shouldn't have told anyone in NPD, but I did anyway.
Oh,
but in college,
we
joked, now they've all heard it, about optical engineers. So in the software, you do really click, you sort of just click one button. That's not really true, but you program a script of how you want it to optimize the system, and then you click that button to run the script. So they say I just sit there all day just hitting the button, and it just does the work for me. But really, and sometimes people joke that it's more programming than actually like a physics thing, because you're designing like a what they call a macro, to actually tell the system what you need to do, and it's going to go in that direction.
Mm-hmm.
So what it does is it's changing curvature of glass. It's changing the glass type, which we'll show this chart eventually. So it's moving around there. Index and Abbey number. Abbey number's dispersion. So the index changing with wavelength. Index is how much optical power, I guess, or how much it's going to bend the light at the glass-air interface. The fancy way of saying it is when the light actually gets to the lens.
Sure, when it touches the glass's surface, right?
Yep. And then you have the spacing between them, and I think that's it.
Okay. So, I mean, when we talk about, like, optimizing an optical system, is that kind of process as a whole what's happening there? Like, you're changing a curvature to do this and a little bit of, focal length and just all those things to work together optimally or not?
More or less.
Ish?
Yeah.
No?
I think that's a good way of saying it. I mean, you have to start kind of from the beginning. You start doing first order things like F number, determining your F number. So what's the objective size? What focal length do you need to capture whatever field of view? Because focal length and field of view are more or less interchangeable. They're not the same thing, but a shorter focal length is a wider field of view. And then you might look at your reticle size. How much travel do you need? Then you kind of work back from there. You have to get your kind of first order thing working.
Yeah.
And from there, then you do the correction like I was talking about. So there's optical aberrations, and then there's also diffraction. Those are the two main things that basically make an optical system not good. Diffraction is light bending around corners, which is sort of weird, but every time you have a finite size like this,
Sure.
instead of if you had an infinitely sized lens, then it would collect all the light and you wouldn't have any diffraction because there's no corner. But now there's an actual edge here.
Oh, okay. Just around the edge of the lens.
Yep. And then, of course, there's a bunch of lenses, so there's diffraction. And then aberration is other properties of lenses, so you can get light coming from one direction versus another direction, focusing in a different spot, which would be astigmatism. And then I'm not going to list all the aberrations. Distortion, which commonly people use as just like the image looks distorted, like blurry.
Just not quite like what they would expect with the naked eye or something.
Yep. And then that's kind of the catch-all phrase, but optically it just means magnification changing with field of view. So the farther out on the field of view is, the more magnification changes, which makes it look barrelly or pin-cushiony are the two.
Or a little bit like fishbowl-y or something.
Yeah. Whatever you want to call it.
Yeah.
And at the end of the day, for the customer, it doesn't matter. They just want to see it flat. So
right.
But
that's exactly.
So however they describe it, just got to figure it out. Figure out what the problem is and then solve it.
Now, from what I've gathered too, as much as people joke, like you just kind of sit, like you were saying, you sit there and you push the button and let the computer do the work.
It's like Enhance on the TV shows.
Exactly. Yeah. From what I've gathered, one of the tricky parts, though, for you optical engineers is going in and saying a computer can come up with any weird lens curvature and shape and spacing that it wants, right? But ultimately, that optical design has to be mechanically created, for one, and then has to mechanically fit together with other things like the turret system, the parallax knob, the zero stop, the reticle, whatever it is. And so sometimes this ideal computer generated thing where you're like, look at this perfect optical system the computer spit out, then that's where the mechanical engineers come in. They're like, well, how are we ever going to make that, or how is that ever going to fit into a scope? So then you have to go in and start sort of making it a little bit more realistic, right?
Yeah, so that's one big difficulty, is making it manufacturable is the way to say it. And then another big issue in just the design, like how the design goes or the process goes, is the software is always making it better. So you tell it what you want and it makes it better, and it'll reach a point where it says it's the best. And then there might actually be something that meets your requirements over here, but to get there, you have to get worse. You have to move through a solution that's worse than to get better. So you get stuck in like a valley. Yeah, it's kind of weird. Without like a diagram, it's
gonna get worse before it's gonna get better, Jim.
Yeah. So this, as far as the software goes, it calculates. Okay, let me like mess with the spacing or the curvatures all a little bit, because you can't. If you make a huge jump, you'll just fly all over the place and never like reach or approach a solution that's good.
Yeah.
So it approaches it. It's maybe changing one curvature a little bit, and it's changing everything, and then it just says I can't get any better. But if you did do like some weird jump, you might move over here and then actually get better, and actually be better off than you were in the other case.
Okay.
Where the solution actually meets your requirements.
Does that also have to do with the fact that there's like, 10 to 14 to whatever lenses in there? So like you might change one, it screws everything up, but you change that to then change another one down the line that would then make it better for that new sort of solution you started doing, right?
Yeah. And this is just not a million. Well, maybe a million. I don't know. A lot of variables. I have to go through and count them, but you're changing so many things at the same time. And so, you can very easily get stuck or like just be searching forever. It's really important that it's kind of like a puzzle solving thing to recognize patterns as they come up and just be moving around. Know when to stop looking at one solution. You're like, okay, this is as good as it's getting. It's not working. It's not good enough. I have to do something else.
Right. So, okay, light transmission. Sorry, we got a little bit off topic of light transmission. Yeah. This is just what happens, folks. But anyway, we talked a bit about objective size because we compared that AMG 624 to a Crossfire 624. Huge difference in price. Numbers can be similar. How about, here's another one that I see sometimes within the same line of scopes, right? So you're looking at like all PST Gen 2s or all, who knows what, Viper somethings. It seems as though I've gathered somewhat of a pattern, and tell me if this is just a coincidence or if there is actually something to this, that the lower magnification you go within the same line, so all else similar, same sort of quality level-ish, lower magnification configuration you go, the better low light performance? Is there something to that? And is that just exit pupil, or is there anything else going on there?
There's always a lot of things going on.
Okay, I should have known. I should have known.
The big thing I think is going back to F number. So for a low power variable, let's say like at 1 to something, you have to have a really short focal length, and then the objective size is something. Although at 1x, it's not use the entrance pupil size. I didn't really mention that yet. We talked about objective size, but really the amount of the objective you're using is the entrance pupil. So you probably already know that like a 1 to 10 doesn't have a 24 millimeter size pupil at 1x. It has something smaller.
Well, a lot of people don't know that because they just hear you just divide.
You divide
the objective size by the magnification, and bink, here comes your exit pupil. But on a 1 to something, that's not the case.
The easiest way to see it is, you just look and you're like, I'm not 24 millimeters off. Or you could just look at, it's shining it on a wall or something.
Sure.
But at the high end magnification, usually you're using the full objective. I hope you are, because then what's the point of having that size if you're not using all of it at some point? So you're using the full objective, and you have a shorter focal length, and you work out some F number. So for like a low power variable, 1 to something, focal length might be around 50 millimeters. The objective might be like 24 millimeters or something. So it's like F2. And then if you look at a higher mag scope, the kind of the focal length increases by a certain amount, but the objective size doesn't increase in that same ratio. So the F number ends up being higher usually.
Okay.
So like I guess if you go to like a 4 to something, the focal length is going to get 4 times longer, but the objective isn't like 80 something or 96 millimeters. It's not 4 times greater. It's only a couple times greater. So the focal ratio is what's really controlling it, and that's lower at the low power variables.
I tell you, we've discussed. I've brought up some of the discussions you see online with people talking about light transmission, and this F number thing that you're bringing up is rarely ever talked about. It's one that I struggle figuring out as well. Like you mentioned, you see it in cameras more, and you'll hear people talk about F whatever,
stop.
and then or F followed by a number. But in rifle scopes, people hardly talk about it.
Yeah.
But it does seem to have this great importance on your field of view and also the sort of low light performance, right?
Yeah. And the thing is so that's all true, but still the other things that I talked about still come into play. So it's hard, even if there's no necessarily like one number where you can say this has better low light performance unless you find a way to incorporate all those things. But is everybody going to do that the same? Probably very low chance.
Right. I mean, and here I am. I'm bringing up the F number like it's like this amazing thing. Like now we know what the one thing is. But I mean, it's the same way people frequently, when they just start getting into optics, start looking at objective bell size. It's like, well, that one's bigger, so it's better. And it's like, well, there's just so many other variables to it. How about when you mention that low power variable? So some people talk about those and they say, well, there's no way, like the Razor Gen 3 1-10, it's got a 24 millimeter objective. Like, why? What's going on there? Because I think there's a Viper HS 2.5 to 10 by 44. That's a whole 20 millimeters bigger objective. On 10 power being its highest power, but we're talking about a scope of 24 millimeters. And you'll see people like, well, the exit pupil is going to be so tiny on that, you won't be able to see a dang thing when it gets even, moderately low light out. How do you make a scope with such a small objective, even other low power variables that are 6 or 8 on the max? How do you make such a small objective do so good in low light? Does that go to the F numbers? Does that go into the lens styles? Does that go into just it is what it is? You don't have to worry about the objective size that much? I don't know.
It's sort of everything. For low light, it does come down to F number. I mean, that's part of it. You got to know how much light you're starting with.
Yeah.
But then, like you said, everything else that comes after that, that's what are you doing with that light in between to make it good on the other side?
Okay.
Because you want to collect as much as possible, but you also want it to be as good quality light as possible in the end.
Use
Usable
what you
light.
got efficiently.
Yeah.
Okay.
And so, like, if you just said, let's maximize the objective size, there's a bunch of consequences to that. I guess the first easy one would be just more aberrations. So your image will be worse generally. Or if you try and spread out, I guess, across the pupil, you're using a bigger objective, you have a bigger exit pupil size. So if you're trying to make it really good across that whole pupil, it's probably degrading the quality across the whole thing to balance it out. Or it's just really bad at the edge and it's not usable.
So you're saying, hold on a second, because I want people to pause and think for a moment. You're saying that actually in the case of, again, we're using the Razor 1-10 by 24, for example, that making it a bigger objective could or would make the image quality worse?
Yes. All else being equal, it would be
all
worse.
All else being equal, right.
And then if you tried to correct for it, it's either more expensive, or if you have to add more lenses, it's going to be heavier, potentially more absorption, less transmission. It's just all these trade-offs happening back and forth.
Yeah.
And so in optical design, you have all these targets, and maybe at the beginning you're gung-ho and you're like, this will be great. And then, but as you go along and all these things are just balancing out, it's like, well, there's no one button that says, I'm just going to crank up the transmission, crank up the objective size. You can mess with it all you want, but
earlier you said there is just one button, though.
There is one button.
Yeah, I like the one button method.
You just hit it.
Yeah.
Enhance.
Yeah, it doesn't work that easy, unfortunately. I wish it did.
It is interesting though. It seems as though well, the objective lens is very important for you guys as an optical engineer, because it's the first point of contact with, or it's the first point of contact that the light makes before it enters the optical system. It reminds me of muzzle velocity when you're shooting long range, because people say, oh, well, why are you guys so worried about, or wind at the muzzle? Everybody, why are you so worried about wind at the muzzle? There's wind all over the place downrange. It's like, well, what's the one that we know about, and what's the first wind that the bullet comes in contact with? Is the one at the muzzle. So that's sort of what it reminds me of. But then it seems like from there, it's on you guys. Does an objective lens size get picked right off the bat, and you say, like, we want it to have this objective lens size? Now, optical engineer, you go and optimize everything behind it? Or are you optimizing everything all together, and then whatever objective lens size gets picked at the end or gets determined at the end is the best? So you're kind of like, well, we ended up with a 24 or a 30 or a 44 or whatever.
This is actually a good question, because it brings up something I should have said earlier, which is the first step to making something good at low light is what you're saying, which is going through customer requirements and deciding what is the scope meant to do. Because there's so many trade-offs and kind of pulling it back and forth, like the blanket analogy of just like stretching it one direction. Is that the direction you want to stretch it? Maybe you do need a bigger objective, and there's a reason behind it. But we do spec out a range. I will usually start with the target, and usually I don't need to deviate from that. But you might leave yourself some room based on the requirement of that optic to, at the end, say, okay, there's not enough. I can't correct enough of the aberration, but I need to meet all these other targets. So I'm just going to reduce the objective size or something.
Mm-hmm.
That usually doesn't happen, but I mean, it can happen. You leave yourself some room, I guess, with every spec.
Yeah.
But I mean, it's in the software. It's usually something you just define. You're saying the input of light looks like this. It has this diameter and it's coming from this angle. So that's just like something you don't define as your starting point.
Right.
If that makes sense.
Mark, have I asked all the right questions to finally get you to believe that objective size isn't the end all be all?
No, Jim. More is better. I was taught that at a very early age.
I know. We're still working on hammering it out of you.
I cannot deviate from that. But no, I mean, it really does. You take the original PST series, right?
Right.
The 2.5 to 10 by 32. Shining star, right? And I'm sure Christian could probably tell us why, but it just seems like that was like a standout. And you're like, 32. Like, kind of like what you're talking about with the 24. Oh, you can never get good light transmission.
Yeah. Good luck after 4 p.m.
Right. And yet it just did very well and kind of a variety from resolution, color, all the good stuff,
Yeah.
Which one was that?
That was the PST Gen 1, 2.5 to 10 by 32.
Should I be buying that?
If you can find
If you
it.
can find one.
You started after that one. So the equivalent now would be the Gen 2, 2 to 10 by 32.
Okay.
But prior to the Gen 2, 2 to 10 by 32, the 2.5 to 10 was
But the
money.
The blanket analogy is such a good one because every time we talk about optics, there's just so much give and take.
Yeah.
And it's just, more isn't always better. And it's just so crazy that you can decrease maybe an objective diameter, which, then people are like, oh my gosh, your light transmission's going out the window.
Right.
But then like so many other things get better. And I guess here's a question that I have. Are there, from the user standpoint, when you're looking through an optic, are there attributes of what the person is seeing that may actually not be light transmission, but it's perceived as this has great low light performance?
Fantastic question.
Sounds like something I shouldn't say. It sounds like
proprietary
a secret.
data, Mark.
I'm
Only
sorry.
we know that.
There's definitely plenty of stuff because humans perceive things differently that you figure out what people like and why, where the number might not indicate that, but it looks better.
Sure.
So
Sure. Well, I mean, okay.
Secret
Eyes
stuff.
are different, right?
Yes.
I mean, our eyes are different than a deer's eye, whatever. So we're just gonna, I guess you're maybe optimizing it for a human being as well.
One, my eyes are different from your eye too.
Right.
How does I forget? I
Oh,
think
yeah.
we chatted about this at one point. I think in the last podcast, but still, like you're trying to make an image that comes out ready for an eye to do the final focusing down under the retina, if I'm not mistaken. How do you deal with just the fact that there's so many different eyes out there? I mean, there's some people with some screwed up eyes. There's some people with really perfect eyes, blue eyes, green eyes. I'm just kidding. That probably doesn't matter. But, there's astigmatisms and all that
What
stuff.
color are your eyes, Jim?
They're just like mud,
Kind of a green.
mud. But how do you deal with that? Are you trying to serve something up where you're like, this will do good with most eyes? Or is there like this perfect eyeball that's like the atomic clock somewhere and it's like the atomic eyeball?
there are models of the eye that I think you can just pull off Google somewhere. Like people have built or made papers or research papers of this is how I modeled the eye. I don't use that necessarily, but
Okay.
there's a lot of, you can do research on the human eye, the healthy human eye, normal human eye, and I think using that as a reference, because you can't make one thing for all people because all people are different, but most people have healthy, normal eyes, I guess.
Sure.
The biggest change, I guess, with age is that focus that we talked about last time. There's certain things that don't change as much with the eye. I guess I'll leave it at that. But
Yeah.
there's definitely a lot of stuff where just researching it, you get a good feeling on it. And then there's all the work of just talking to other people, talking to a lot of the employees here, which is just the biggest benefit as an optical engineer. You just go to talk to someone who's shooting a PRS match all the time or something, or 3-gun, or just out west hunting all the time. Hey, what is your opinion on this? And then just try and translate it into the design, make the connection between feedback and the physics.
If you heard me talking about image quality in an optic, I'd be saying, like, man, it's really like, it's easy to get behind. The image feels like super flat and it's really crisp. Are you in your head hearing like these phrases I'm giving you and you're like, well, that's because the F number's like this and the curvature's like that, or I could tweak this to get this better perception of that? Or is that how you think, or are you think
sometimes if there's like something that I could pick out from what someone said quickly, where I'm like, okay, that was something I was already thinking about.
Okay.
And it's confirming something I thought. A lot of time my mind's just blank. Like if they're saying it's good, it's like, sweet.
My job is done here.
A lot of the dirty stuff is when I'm just like focused on the computer once I'm in the zone.
Sure.
And then at the end of the day, my brain is just shot because I've focused too hard for too long. But like when I'm in front of the computer, I'm thinking about all that stuff, and then I'll ask questions when I'm in the middle of something. But if you were just next to me, you're like, oh, this looks clear, I'll be like, sweet.
Sounds good. I'm glad.
I might space out.
Mission accomplished.
Okay, so let's say you make an optic good. So a lot of what we're talking about, again, light transmission comes up. People think low light a lot. Let's say you're making an optic and you're just making it just good, right? So it's just when you look through it in the daytime, it looks great. Is an optic that you just make really good, just naturally good in low light? Or would there be a way some optical engineer could literally go in and be like, this optic is going to be terrible in the daytime, but it is going to be amazing in low light? Or is low light performance just a result of just a good optic?
It generally will make it better.
Okay.
If you wanted me to, I could probably do some really messed up stuff to make it like that.
Make it like during the day, I'm like, I can't see anything. And then it turns night and I'm like, I've got X-ray vision.
Maybe not quite to that extent, but yeah, pretty close.
Interesting.
Like that doesn't seem like it would be even possible. Like how could those things work opposingly?
This guy bends the light.
I'll tell you later. I'll tell you later.
Light bender.
But yeah, generally, so if you correct the scope to be just high resolution in the day, it's going to be better at night. I mean, you could just think of it as like if it was really blurry during the day, it's also going to be blurry at night. And if it's clear in the day, it's going to be clearer than it was before at night when it was blurry.
Yeah.
But that doesn't necessarily mean you're like all those other things are in line for transmission. Like we talked about minimizing stray light, which might affect how you're looking at the scene.
Okay.
And all those things. So,
and define stray light again, real quick.
It is light more or less entering your eye that's not supposed to.
And is that through the scope, or is that from just like the sun at a low angle coming from outside the scope?
It can
be.
It can actually be both. Yeah. So it could be the sun in your field of view, and it's not interacting with the scope. It's just in your field of view. Sort of like if you're go back to the phone camera because it's easy. Like it overexposes, or like it tries to mess with the exposure for that spot, but then you wash out something else in the image. It's kind of the same thing with the human eye. It's called dynamic range. So like it has to do with like the brightest thing and the darkest thing you can see. But if your eye is like adjusted for having the sun right there, then when you're looking through the scope, it's going to look differently than if the sun wasn't there.
Yeah.
But then there's also light if the sun's behind you and it's just bouncing off maybe the eyepiece that can do it. And then it can come in, it could actually come through the glass there and bounce off a mechanical surface, or it can come through the front. Like if the sun was at an angle, that's what the sunshade's doing. You're not really changing objective size, but you're kind of blocking any extra light that can come through. But you can get light just bouncing around and coming through. Sometimes you can get like, they look like kind of like images or like flares or ghosts is what you call them, just like maybe a bright spot or like a weird streak of color.
Sure.
Anything
I remember like there's been some prototype units that have come through in the past where you're working on different optical systems and, you're looking through and everything looks amazing, and then you get it. And this is something that we describe to a lot of customers too. Any time that you're putting yourself in like a really low angle sun where like the sun is right there on the horizon or right there on the horizon behind you or something like that, and it is going to do that, you have the chance for these things to happen. But yeah, like some prototypes and stuff, it's like, wow, this thing's amazing. We're about ready to push go, and then you pan it over and the sun's a little bit lower in the sky. And you're like, whoa, like this thing just comes out at you and it's like, whoop, back to the drawing board.
Yep.
But yeah,
It takes a lot of control. It's mostly a mechanical design, but it's kind of mechanical and optical working together.
We won't let the mechanical guys know that you said that, by the way.
it sounds like they already heard the last one, so there's already some shade.
Yeah.
Another thing you said that I was super curious about, you kind of alluded to it earlier, but talking about exit pupil. So exit pupil is another one that people get super stoked about because they think to themselves, well, you got how much your pupil can dilate, and then if you're using up, let's say your pupil's dilated to 4 millimeters. Well, if you've got 4 millimeters worth of an exit pupil there, then you're utilizing all of your available pupil to suck in light to your eyeball.
Yeah.
And then if you just have this big exit pupil, that's going to help, especially when it gets low light, because when it gets low light, your eye's pupil dilates a ton, and so you want to use as much of that as possible. One thing that you mentioned, though, was that let's say you've got a lot of aberrations or the edge of your sort of field of view through the scope isn't that great. Getting a big old exit pupil isn't necessarily going to help you because you're only going to use up a lot of that exit pupil with a less than ideal image.
Yeah.
You may have
that's right.
like a 5 millimeter exit pupil, but only 3 of it is really good or something, just to throw some numbers around.
No, that's a good way to think about it. I mean, if you're going to let light through, it better be good light, I guess, or usable light. If it was just completely blurry in an extreme case and you could resolve nothing, then why let it through if it's not giving you any useful information?
Yeah.
That's a good way to think about it. And that's something that's not going to be captured in like your basic first order spec sheet on a website.
Yeah, I mean, you look at it on paper and you just see exit pupil.
Yeah.
It's just a number. That one's bigger than that one. Better.
Yeah.
Very interesting stuff.
That's all interesting stuff, Jim.
What is this sheet, by the way, you brought out earlier?
Just
Let me
gonna
roll up my
ask.
sleeves.
This is the optical glass chart.
Looks like
Should we hold it up?
Yeah.
I think we can. Yeah, we can hold it up here for the camera. It's essentially we have SFPL, SFSL. We got one that says SLAM.
Yeah. My favorite just because of the name.
Right.
So this is one glass manufacturer's glass chart. It's nice because it's laminated, and they gave it to me for free at a trade show a couple years ago. So it's also very descriptive. So they
best eye chart or glass chart for the money.
They have some good information. So they have melt frequency, which is how often are they making the glass, and then they have the relative price to the benchmark, which is the most common glass, which is BK7 if it's shot, and then this one's BSL7. They're, I think, more or less the same chemical formula. Basically, every single shape, there's all these little shapes. You may not be able to see it really great, but they're all different glass types.
Yeah.
That this manufacturer makes. And before I was talking about Abbey number, so this is the Abbey number part of the plot, and then this is the index. So high index would be it bends light more, and then low Abbey number would be higher dispersion. It's just kind of backwards, but higher dispersion means it separates colors more.
Okay.
So you can use that in color correction because all the glass is going to separate colors to some amount. And optical design, it's not like making every lens perfect individually. You're making something that's well balanced to make it work throughout the whole thing.
Sure.
And let's see. The other thing is, so crown glasses are down here, and flint glasses are up here.
Crown. That
crown
sounds
and
nice.
flint. So usually what's called an achromatic doublet, which is correcting color. You cement two pieces of glass together. You use it, crown and a flint. I mean, you can use whatever glass you want, but like the classic optical lesson would be calculating out the indices or indexes of refraction and making two wavelengths come together and use a crown and a flint to do it.
Right.
It's like some of the first things you learn. So that's kind of it. And then all these names are all these like little or bigger shapes, I guess, are the different chemical formula sections, more or less. I think they're similar chemical compositions. They modify it, and then you get different glasses in that area. So it's pretty descriptive, but...
So, like, somebody makes a scope or whatever, and people are out there talking on the interwebs, and they say, well, what makes this one better? And they say, it's got better glass. So are some of these in here better than others? I'm kind of that's like a question I sort of think I know the answer to, because I'm pretty sure that
You just want me to say it.
I do. I just want you to say, because if I say it, everyone's like, yeah, it's just Jimmy's full. You know what? Anyway, but
Yeah, there's not really better glass. There are some glasses that are expensive and might be useful, but really, again, Dave has a good analogy for this. It's like a chef, and you can have really expensive ingredients, but if you suck at cooking, it's still gonna taste like crap. So, there are glasses that have their uses that some glasses might not be able to do, but it doesn't necessarily make it better. It's really
Sure.
more about the design than anything.
yeah,
Especially manufacturer to manufacturer, there's definitely no quality difference. So, like on a lens drawing, you get to the stage where you're making something, you have a drawing of the lens, and you send it to the manufacturer. You're going to list a glass type and probably put like or alternative, because there's so many manufacturers that make the same thing more or less.
Okay.
That's basically equivalent. One of the reasons you do that is they could discontinue any glass at any time. So let's say you have
There
a
you go.
design, a year later they discontinue it. They will keep stock for a while, but they might stop making it. And at a certain point, maybe it becomes too expensive and you have to switch to an alternative manufacturer and they're making it. Usually you just leave that up to the lens maker. I mean, you just tell them or alternative, and they'll find the cheapest alternative to save the most money for the customer. But it's all going to be the same anyway.
right.
If you really wanted one specific company, you could tell them that, but you'll just pay more, or they won't. Sometimes they just don't have it available at that time.
Yeah, it might take longer or whatever.
Yeah. So it's certainly a trade-off if you wanted to use one manufacturer, but like I said, that's not really better. You don't get any benefit from that.
Yeah, it's about using the right glass
Yeah.
for the equation that you have.
Yeah.
So you might use different glass at different times, and
Yeah, like basically all these are fair game. The biggest thing that I would look for in terms of, I wouldn't say it's a better glass, but things that are being made more often and are cheaper are, if you're able to use them, the only reason they're cheaper is just the chemical composition or because it's in high demand. So like, let's say a car's backup camera uses a lens in that camera that gets used in every single camera of all their models, then it's going to be really cheap for me too, because they're ordering a bunch of it and it's always available because they have to make it for a really high volume application, millions and millions of cars. So
that makes sense.
it's not really better optically, but it is better for the customer to get them
Yeah.
a cheaper option
Yeah.
if you can do it. But a lot of times you can get to a solution where it might be sensitive to try and change to a different glass type, might do that jump, like I was saying, into a different solution where maybe it doesn't work anymore. So that's one whole part of optical design. You actually start without any real glasses. You start with just glass models, and it'll just pick not random numbers, but it'll move dynamically. It won't choose these points. And then at a certain point, you have to start assigning them to real glasses, because eventually it has to get made.
Oh, your computer starts making up glass, like at first? And
Yeah,
you have
at
to, like,
first-
find the closest thing to...
Yeah, it does the index and the Abby number.
Oh, I
it's
get it.
on this
Okay.
plot. So it's moving. It might be
Okay.
up here, just a random example, and then eventually you're going to have to say, make it that glass, but now you're moving and you are doing a jump, so that is its own part of the design.
I'm trying to think of, like, what's that? Oh, I don't know. I'm gonna screw it up, so I'm not even gonna try and take too much time. But it's like one of those games where you keep trying to get it just right, but then every time you change one thing, you screw up the whole rest of the thing, and then you shoot, I gotta start over again. But
House of Cards,
could be.
knock over the whole thing.
But yeah, it does sound like quite a process, and I just think I like talking to optical engineers about this stuff, especially just because I think there is this element of sort of having to trust what the optical engineers come up with, and then also understanding sort of what you have bought into, you know. So I
Yeah.
think if you buy the cheapest optic that you can find ever, and then it doesn't do what you want it to do, understand that optical engineer, whoever made it up, was dealing with, you know, they were significantly hamstrung by whatever they had to have the final product come out like, you know, in terms of quality and value, and they had to probably make some what's the word, sacrifices in certain areas that they otherwise wouldn't have wanted to. And then with a more expensive optic, that's where you get the chance to play around with different, curvatures. I'm sure when they're making the lenses or different glass types. But you see so many people out there when they see an optic, before ever even a lot of times looking through it, it's just like, well, the objective's too small, or the magnification whatever is wrong, or something like that. They make out some little point based on a number on a spec sheet, and it's like there's a lot more that goes into it than the numbers you get on the spec sheet. I'm sure if people saw a spec sheet that had all the numbers that you have, that about the whole optical system, it would just be they wouldn't even know how to sift through the thing.
Yeah, and actually a lot of time. So it's funny because you have to trust the optical engineer to an extent, and a lot of the guys in NPD will be looking over my shoulder and be like, I have no idea what you're doing. Or sometimes they'll say, I'm really glad you know how to do that because that looks crazy. And the same way, like for mechanical guys, they could probably learn the optical design software in some number of years if they really worked at it, and I could probably learn SolidWorks and do solid modeling in a few years, but I don't want to. So I'm really glad that they'll do it.
Right. That's cool. Go through my questions here, Marco. Did you have any other ones?
Well, I mean, I saw that you had one, and this is one we've talked about before.
Yeah.
But since we have the example of a rifle scope here, and we're talking light transmission, I'd say, a common misconception that folks might have, and intuitively, I'd say the same thing, but for instance, 34 millimeter tube on this rifle scope here.
Thank you.
Oh,
that was the one I missed.
More light transmission, more lights getting through that big tube.
Bigger tube.
Christian?
Yeah, not really true. Yeah.
The tube?
Incorrect.
I was thinking of all the details I could go through. I mean, there are definitely things that it helps with. You can fit a bigger lens in there, but that's really it's not really pupil, which is kind of what we're talking about. It's more field of view, and the bigger field of view and bigger actual mechanical movement means you have more travel. I mean, that's really the biggest thing.
Right.
So, like, there's an example of, like you just said, like a bigger lens inside of where the tube area. So you're talking about the Erector system?
Yeah.
Kind of is where you'd have a bigger lens, which is sort of this area that your ring's usually attached to is kind of where the bulk of your Erector system is, especially between the mag ring and the turret saddle about.
What I was talking about is more lenses in this part of the tube.
Oh, okay, up forward a
you
little
are
bit.
actually limited by this size because the Erector tube's all smaller than the tube anyway.
Right, I was going to say, that's usually not where I'd expect to...
So I'm talking about lenses probably in here. And if it's bigger, you can basically... Like the edge of the field of view is coming, and then it's towards the top of the tube here, and then making a big image here, and the Erector tube's just moving in that image. So you can basically get a bigger image and move farther and get more travel, or you could get more field of view if you want. But.
That's right. Let's talk about that for a second, because the image itself, and when you were talking about that bigger lens, you were saying essentially the area between the turret saddle and the objective bell, almost kind of where the objective bell starts to flare out from the tube a little bit, just for those listening, not seeing on video.
Yeah.
So, but okay, that's a weird thing that always trips me up that I forget about, is that you have the image of what you're seeing, the scene downrange that you look through the rifle scope, and it comes through some lenses. You would know what they are, but I just know there's some lenses under there. And then the Erector tube, essentially, in the first focal plane area, is right kind of where that the first focal plane is the first spot where the image is an image, right? Like inside the rifle scope. And the image is usually bigger than the Erector tube. Am I right in saying that? And so the Erector tube is almost like if you had a regular sheet of paper on the table and you had a magnifying glass. Tell me if I'm wrong. But if you had a magnifying glass and you were looking at individual things on the piece of paper, the paper isn't changing in size, or the paper isn't following the magnifying glass. It's staying there. It's the magnifying glass that you're moving around the piece of paper and using to look at different individual parts of the piece of paper.
Yep.
And isn't that kind of what you're doing as you're sort of moving your turrets and you're moving the Erector unit around? You're just kind of moving it around to different places on this image that's staying still.
Yeah, that's exactly right.
And then that gets into where some people talk a lot about travel and things. Usually out at the very, very edges of that image is where you have more of your aberrations or less ideal optical characteristics, or way out on the edges of that image, right?
Yeah, most aberrations scale with field of view.
Okay.
So the bigger the field of view, the more aberration scaling there is.
Okay. So then if you have your erector unit somewhere, if you're, let's say, zeroed in the center of your travel, you're looking more at like the center ideal part of that image. And then some people, like I know some people will say, let's say a scope has 100 MOA of elevation or whatever. And assuming a perfect rifle, perfect everything, right, you zero right in the dead center of that travel. So you've got 50 up and 50 down. Well, they'll say, well, I should go and get a 50 MOA base so that way I can zero my image way, way at the very top of the travel, and then I have all this travel down for shooting out at super long distances or whatever I have, any travel at my disposal. The problem is then you're kind of zeroed up in this sort of like very edge of the periphery of the image. It's not going to be ideal, right?
Yeah. Yeah, it's going to be some amount worse. I mean, that kind of depends on how much correction you do for the field of view.
Sure.
Which, I mean, there's always just like this long chain of variables that you just affected anytime you change anything with the optics. But yeah,
Right.
Yeah.
if you do that, if you zero at the top, you're absolutely right. It's going to be worse off than zeroing at the center, which might not be a bad trade-off. I mean, if that's what you want to do, but
Something to be aware of.
yeah, it's something to
At
definitely
least.
be
And
aware
it's not
of.
always like, you don't always get to the edge and you're like, oh my gosh, you can't see anything. But it is a little bit like, yeah, it's not as good as it was when I was more centered up in the travel.
Right. Well, I suppose the same thing could happen if you had a rifle that, maybe just had some alignment issues, and then you've used up a lot of your travel one way or another.
Yep.
To get it, even just to get a zero, you don't even plan on dialing your
right.
elevation, right?
Yeah.
But you just kind of end up on one of those outer edges, and
Seen that many times. Although I think sometimes, I can't remember if you said it or somebody else, sometimes a rifle scope manufacturer will put in almost like a stop so that it won't allow the turrets to like really push it out there to where like all of a sudden I can't see, like literally it's black, like I can't see anything.
Yeah. Yeah,
Okay.
instead of just kind of riding. Because you
okay.
could, I mean, I'm not the mechanical guy, so maybe I shouldn't talk too much. But I mean, you could really just knock the scope tube, I guess, or you could limit it however you want. But yeah, sometimes you just have like a rectangle or a square, depending on, and then you're not riding along a scope tube wall or something, and it's a lot more consistent.
that makes sense.
The other thing too is, so just going off the point you just said, if someone says I want like the widest field of view and the most travel over anything else, that field of view plus travel, I mean, it just means you're asking for 2 extra field of views. So now it's extra big. So that means towards the edge of the travel, it's getting worse and worse. I mean, so either you have to just correct it way more, it's going to be way more expensive, more lenses, so maybe heavier. Maybe you have to add on length or something.
Yeah.
But it's just, anytime you ask for something, you're probably affecting something else negatively. You're just pulling one direction.
Yeah. So I guess, yeah, if you get a big field of view where you are at your eye behind the rifle scope, it's almost like your erector unit has to be taking a bigger snippet out of that image, right? It's not necessarily that the image itself is bigger, which probably couldn't hurt, especially if you have more travel, but then actually your erector unit and all the lenses behind it have to be able to take like a bigger swatch out of that image if you're getting this big field of view at your eye.
Which means you've got less travel. So then you have to add that much extra travel to get back to the same and then plus. So
okay, that's where you're asking for 2 bigger field of views kind of thing, like you were saying, comes into play.
And that's where like a 34 millimeter tube makes a lot of sense when you're like, well, I want a bigger field of view, but I either don't want to sacrifice travel or I want more, that you really eventually have to just get a bigger tube size.
It makes sense now.
Yeah.
Finally makes sense. Marco, does it
all
make
come
sense for
together.
you?
I might have to re-listen to this podcast.
Oh, man. Light, though. How
She's
about
tricky.
tricky son of a gun?
There's no free lunch when it comes to optics, at least optical design.
That's for sure. That's for sure. Do you ever I'm sure like when you were first starting out in this, maybe you used to just make like the perfect optical system ultimately. Look how perfect it is. And then, how unmanufacturable it is. And is it like, what's that like? You must know what it would be like to get like this perfect optical image. And then you're just like, oh, but it's impossible.
So I didn't go through that as much because I took a really long time. So
Okay.
in the end, I don't think there was really much feedback on like it being not manufacturable.
Yeah.
So that was good, but there's definitely been points before that point. There was points along the way where I thought it was better than it was, and just got feedback from other people. So like Will, the other optical engineer,
Yeah.
he helped a lot. So him and Kaylin as well, and they'll just be like, maybe you should look at changing the geometry of that lens because it might be not manufacturable. So I guess I never got to the point because I had them to help.
Yeah.
But I don't think I had too many crazy things. But as you go, you're just always learning. So you get to a point where you think this is the best thing ever. And then a year later, you're like, I've learned so much stuff about how I can control things better or ask a better thing of the software. If you ask it extra nice, it might actually do it for you.
Oh, yeah.
Well, why didn't you just ask?
Yeah. There have been times where I've like programmed something and I'm like, it's not going to work. And then it works. I'm like, oh, well, I could have just asked. Like, why didn't I just ask?
Simple as that.
Yeah, there's definitely times where either you think you have the best thing, quickly you prove yourself wrong, though.
Yeah.
As long as you're always learning.
Somebody asked in the last podcast that you were on, like, where does somebody actually go to school to, like, make optical systems like this?
There's a few schools. It's either University of Arizona or Arizona State. I'm pretty sure it's University of Arizona.
Okay.
Optical engineers that went there will get mad at me for not knowing which. But they have a huge optics program. I think they have like the #1 graduate program in the U.S.
Oh, okay.
Oh, wow.
Like one of my friends I graduated with college, undergrad, he went there for a graduate. He's just getting his PhD. There's Rochester, New York. They have a school that also has an optics program. I went to Rose Holman in Terre Haute, Indiana.
Oh, okay.
Where Larry Bird, I think, grew up there. Or he
Mr.
there,
Bird
lived there
himself.
for a while, yeah.
Or at least he went to Indiana State. Is that where Indiana State's at?
Yeah, it's like 15 minutes away.
Yeah. Well, he's from French Lick. I'm sorry. He's the hick from French Lick.
Yeah.
He went to Terre Haute. I should know. I got a lot of family from Indiana, so a lot was riding on that. But
Yeah.
That Larry Bird, tough to beat.
That's right.
I think there's other schools you just probably have to Google it. And there's not very many, which is weird. I think it's growing because it's basically in every technology in some way.
Sure.
And there's just so many things that people don't realize that optics gets used for.
Yeah.
That you need to take things to the next level. The speed of light versus the speed of anything else.
Like every sensor ever is using optics, right?
Yeah.
I mean, when you back up and your car goes beep, 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 I mean, that's an optic in there, right?
Yeah.
It's a focal optic, not afocal like these. When you go to school for this stuff, do they even talk about rifle scopes much, or is it more just talking about like glass and light in general? Is it like real and then you kind of have to specially apply it to whatever you're going to do?
I don't think we ever did rifle scopes or any sporting optic, but we definitely did afocal optics, but definitely wasn't the focus. The focus is usually focal stuff.
Yeah.
A lot of focal and focuses. So like a camera is a little bit easier to understand maybe. I'm not sure if that's why. But a lot of the lessons from cameras, like I always mention it, are kind of applicable. I mean, it's the same physics. Your input and output's a little different, but similar stuff's happening, especially in rifle scopes. I mean, you are making an image twice. Mm-hmm. So a lot of the same things are happening. There's so many other weird optics you can do. Like, I remember we did like a spectrometer project where you're measuring the amount of light at each wavelength. So like you're talking about transmission being different at each wavelength. The way you can measure that is a spectrometer. Mm-hmm. So you look at light going through, how much at each wavelength is left over. So we designed one where you separate out the wavelengths and then like put them into a detector where you can. It was weird, but we did a pretty wide range of projects, which makes it also tough. Like going back, you kind of wish you could just focus only on lens design because that's like a lot of what I do now is designing the lenses. But also experiencing that other stuff does, sometimes you don't realize it, but it makes you know and understand stuff that's applicable here that you just don't realize in the moment.
Yeah.
So I don't know.
That's awesome.
But there's probably other schools. Any program of optics I'd recommend, really, because optics is the best. But I'm not biased, but
optics is the best. You heard it here, folks.
It's controlled chaos for sure.
Sounds like it. It's uncontrolled chaos in my brain every time someone tries to explain it.
Yes. That's my goal, is to break your guys' brains every time.
Appreciate that.
Well done, sir. Well done.
Indeed. All right. Mark, you good?
I'm good. I think I'm leaving
good.
with more questions than answers at this point. But
okay.
like I said, I'm going to give this a re-listen.
Sounds like a typical conversation with the optical engineers around here. Yeah, so with that being said, I guess if you have any questions, hit us up. We'll try to answer them. As Christian said, sometimes there's some things that we can't answer because we're an optics company. You got to have some competitive advantage here and there. But anyway, we'll try and answer them. Hit us up on Instagram, in the YouTube comments, whatever works. But yeah, Christian, thanks again for joining us.
Yeah, no
Thanks,
problem.
man. Awesome.
Thanks for having me.
All right, we'll catch you guys next time.
See you guys.
Bye. All right, that'll wrap it up for this episode of the Vortex Nation podcast. Thanks, everybody, for listening. Hit that subscribe button so you can always stay up to date on the latest happenings over here at the Vortex Nation podcast. You can also follow us on Instagram at Vortex Nation Podcast. Again, everybody, thanks, and happy hunting and shooting. We appreciate it. Have a good one.